You've probably seen something like this before. Fluorescence works by exciting a fluorescent molecule with a specific color of light. Then, light with a slightly shifted color is emitted, which we can use filters to isolate and detect. These light energies are characterized by their spectra, the excitation and emission curves for that specific molecule, rhodamine in this case.
But let's use a different perspective. After a 2-year break from college to earn medals of valor and courage on the battlefields of World War I, Alexander Jablonski earned his PhD in physics and dedicated his scientific career to the study of fluorescence. He understood that excitation photons must carry precisely the right energy to bump the fluorescent molecule's electrons into a higher orbital state. He also saw emission as a separate process, one that generated a new photon with a different color than the excitation light.
We can visualize this as he may have with a very simple representation of an electron cloud of a chromophore, the fluorescent structure of the molecule. We see the excitation photons like hammers, knocking the electrons into an outer orbit. The photon was absorbed by the electron like a car wreck, knocking it across the highway into another lane, knocking it into a higher energy state.
But an electron can't hang out in this high energy state long, only a few nanoseconds before the electron naturally relaxes back to its ground state, shedding the excess energy as an emitted photon. Those are the photons we are trying to image. If we can isolate those photons, we can isolate our fluorescence, thereby isolating our labeled latent ridge detail.
Jablonski described this in a visual representation, now known as the Jablonski Diagram. This diagram depicts electron transitions during the fluorescence process, beginning with excitation by the excitation light.
Then there's this vibrational phase. This is a settling of the electron orbit to the S1 excitation state after being violently impacted by the photon. This vibrational settling results in a small energy loss as heat. When the electron relaxes to the ground state again, the energy it must shed is less than the energy it absorbed, owing to the small amount of energy lost as heat.
Remember, the emitted photon must account for the energy from the absorbed photon. But here's the key. When the electron was first excited, molecular vibrations dissipated some of that energy as heat before emission could occur. So the electron doesn't need to release as much energy when it relaxes. Some has already left the system. This energy deficit is what causes the color shift. The emitted photon has less energy than the absorbed one, which means a longer wavelength and a different color.
The Jablonski diagram visualizes this whole process, energy in, energy out, almost like a schematic of a pump. It shows the photons we put into the system and the new photons we get out. We'll refer back to these principles throughout the year as we explore fluorescence imaging in detail.